So today I would like to talk about bimanual manipulation, complex human life, and efficient manipulation. And this shows our team members, and I and Professor Wei Wang and Keisuke Koyama and Takuya Kyokawa are the members of the robotic manipulation research group of Osaka University. And we are collaborating with the automation research team of AIST, headed by Professor Yukiya Domai. And these are our robots in the laboratory, and we have plenty of diorama robots. And I would like to start my talk from the manipulation planning in general. And as you may know, there is a Folilation structure of configuration space in manipulation planning. And the first line shows the transit is so-called the transit path. And in the transit path, the robot manipulator moves with keeping the same placement posture of the object. And the second one is so-called the transfer path. In this path, the robot moves the object with keeping the same grasping configuration. And the third one is not allowed path, like this. And in general manipulation planning problem, we first obtain the common space between the grasp space and the placement space and connect them by using the edges. And in 2014, we have extended this structure for bimanual manipulation. And in this case, the blue one is the configuration space of the right arm, and the green one is the configuration space of the left arm. And the red one is the placement space. And the common space between the blue one and the green one is the bimanual space. And then we can assume the initial grasp and the intermediate grasp and the target place. And on the right arm and left arm and the bimanual grasp space. And with this structure, we can obtain several manipulation styles. The first one is a single arm manipulation, where the robot manipulator places the object and will grasp using the right hand. And in the second case, the robot places the object with the right hand, then we grasp it from right to left and place the object to the designated posture by using the left arm. And in the final case, the robot will grasp the object from the right to left. Okay, then in 2014, we have applied into the real world scenarios. And in this case, the work is placed on the box, and the robot randomly picks one of the objects from the box, and we grasp it to the left arm and place it into the jail. And in this experiment, we use the grasp planning to plan the grasping. And we consider regrasp planning. And we apply the trajectory planning to avoid the collision with the obstacles. And later, our company applied this system to the real environment, real factory. And this system has been used in the real factory. And now let us review when bimanual manipulation is used. We can roughly assume 4 situations. One is complex manipulation. And second is the large object manipulation. And third one is the learning from human manipulation. Since human had 2 hands, we have to necessarily use the bimanual manipulation if we learn from the human manipulation. And the fourth one is making task efficient. And first, I would like to explain about the complex manipulation. And in this case, and in the video in the left-hand side, a human worker is trying to assemble the oil sealing to the cylinder. This is a highly complex and skillful task. And in the right-hand side, we applied the motion planner to this problem. And in this case, we use the optimization-based planner. And we assume the index function composed of the collision avoidance and minimizing the elastic energy. And we can realize such manipulation of an elastic ring. And next, I would like to explain about the extraction of an item from shelf, especially in logistics. There are a lot of items randomly stored in a shelf, and the human worker has to extract one item from the shelf. But this is a very highly skillful task and very, very difficult for robot to perform. And in this case, humans usually extract one of the items while supporting the other items by using other hands. And we have constructed the prediction. We have predicted when the pile collapses. The middle one is the depth image of the pile. And first, we segment and binarize, and we can obtain the image like this. And first, we assume we extract one of the item from the shelf while supporting the one another item in the pile. Then, by using the neural network, we will predict whether the pile will collapse or not. And this is the overview of a neural network. And to train the neural network, we use the physics simulator. And this is the experimental result. In this case, the robot determined to support this item and then extract this item. And then capture the depth image and support this item and extract this item. This is a more complex case. Support this item and extract this item. Like this. And the second, I would like to explain about the motion planning and the constraint from the cables. when robot manipulates, robot uses the mechanical tool, we have to take care of the entanglement of the cable with the arm. So in this video, the robot pick up the suction tool, but the cable entangled with the other tools on the table. So we use the other arm to hold the cable to avoid the entanglement of the cable with the arm. So this is the video showing the case where the manipulation planner is applied. Okay. And third one is the assembly planner, taking into constraint of the gravity, coming from the gravity. So in this case, the robot tried to assemble a soma block. But while the robot tried to assemble the soma block, we have to take into account the constraint coming from the gravity. But in this case, if the robot in the left-hand side release the object collapse. So the robot has to keep grasping the object. Then if the right-hand side arm assemble the object on top of the other one, then the arm in the left-hand side can release the object. So in this case, also the assembly planner, task and motion planner is used along with the constraint coming from the gravity force. Okay. And then let us move on to the topic of large object manipulation. And the first one, I would like to explain about the feedback control of pivoting gate, considering two gate modes. Maybe you are aware of the pivoting gate, but there are two gate modes in the pivoting gate. One is so-called the QS mode. In this case, the face of the object making contact with the table. And the other one is the DS mode, where the object does not make face contact with the object, with the table. And the essence of this research is that the QS mode is more stable than the DS mode. So the robot effectively use QS mode to keep balance of the object. And if the object is light, the external disturbance is light, the robot can keep balance. The robot can keep the DS mode, but the object becomes heavy, it becomes impossible. So the robot once use QS mode to keep stability of the object. So in this case, the vision sensor watches the motion of the object and gives the real-time feedback to the robot. And the second one is so-called gravitational caging. And in 2D caging, we usually require 3 fingers, but if we assume the gravity force, we can use 2 fingers to satisfy the caging grasp. So under this assumption, we realize the manipulation of a large object by using the dual manipulators. And later, we will have a time for poster presentation. And please visit the poster presentation of gravitational caging. Then I would like to move on to the learning from human manipulation. And this is, in this video, we show the situation where a human teaches the robot how to assemble the product. And the human operator wear the head-mount display, and the motion of the human hand is tracked. And the motion of the human hand synchronizes with the motion of the dual manipulator in the virtual world. And then the human operator tries to assemble the object in the virtual world. Then the motion of human operator assemble a product is recorded, and replayed in the real world. And this is another example of using human demonstration for manipulation planner. In this case, a human operator teaches the robot how to use the mechanical tool. And in this case, we use screwing tool. The position, the robot record, the robot memorizes the position and orientation of the mechanical tool. And then plan the manipulation motion of using the mechanical tool. And this is the result of applying the motion planner. If the mechanical tool is not reachable, the robot automatically regrasps the mechanical tool and performs the target task. But when we use such approach, it becomes difficult to precisely adjust the position of the mechanical tool. So we use the force controller to robustly perform the required task. So we use spiral search to search for the position of the hole. And lastly, we would like to explain about how to make task efficient by using the bimanual manipulation. And in this research, we consider constructing the assembly motion from graphical instruction manual. And we show the graphic instruction manual in the left-hand side. And then in the right-hand side, we show the constructed assembly task sequence graph. And from each illust of the instruction manual, we can construct the element of the graph like this. And then finally, by combining the element of graph, we can construct the whole sequence of the assembly graph. Here, we assume the bimanual manipulator to perform the task. So each graph element is placed in parallel. The task can be allocated in either right or left arm. And in this case, in case of this research, if the object is placed in the left-hand side, we use left arm to perform the task. On the other hand, if the object either part is placed in the right-hand side, we use the arm in the right-hand side. And then we can simultaneously perform the task by using the left and right arm. So in this video, left-hand side shows the robot performing the task. On the right-hand side, we show the instruction manual and the constructed assembly sequence graph. And finally, I would like to show the robot motion planning based on the cooking recipe. And we use the same method to assign the task to the right and left arm. So in this case, the cooking recipe is cut a potato and put it into a bowl. And from this instruction, we constructed the assembly task graph. And then robot moves according to the task sequence graph. And in this case, the instruction is to heat a fry pan and grill the pork. And from this instruction, we constructed the task sequence graph. And then from the task sequence graph, the bimanual manipulation is constructed.